In this video, we're going to take a look at the area of surfaces of a revolution. And so I'm just going to jump right into the formula on this one, because the last video, when we did the arc length, that really set up most of the hard concrete work we had to do to create this. So we'll break this down after we define it. The area of a surface generated by revolving the continuous differentiable function y equals f of x on the interval a to b about the x-axis is, surface is equal to the integral from a to b, 2 pi f of x times the square root of 1 plus f prime of x squared dx. Or if we want to use the y notation, we can replace that f of x with y, and then y prime becomes dy dx. Now, right away, something should be jumping out to you. The square root portion looks very similar to the arc length. Like I said, we did all the hard work in that video. So there is clearly an element to the arc length in this equation. So let's think about why that would be. Let's say that we have some sort of continuous function, right, differentiable function, and I'm going to rotate that about the x-axis. And so down here, once we rotate it, we'd have that same sort of picture. They would be parallel in every respect. So if I were to take this thing and just kind of look at that shape, that is the shape that we're getting as we revolve that thing. That is the exterior of that shape. And so if we think about how to find an area, it's the length times the width. Well, this length right here is the arc length that we found in the last video. And then this amount right here would be y, but because it is remember, because it's a revolution, it's really that idea of a circle, so it is 2 pi y, because we need to think of this as the circumference, right? Because it's, as it rings around, that height element would be the 2 pi y if we were to kind of slice it and then unwind it. So kind of the idea of taking the wrap around a Coke can, cutting it in half, and then laying it out flat. That's what we've done here. This element here is just the arc length, and then the way around, that is a circumference, so 2 pi times the radius given to us by the element y. And that is where our formula is coming from. That's where we're getting that from. So let's just jump right into an example. So let's find the area generated by revolving the curve y equals the square root of x, and x is between 3/4 and 15/4 about the x-axis. Now, as we've said in the last 50 videos, that's an exaggeration, but as we've said in about every video in this class, we are going to start with our picture. It is always a good idea to get an idea of what we're looking at. So the square root of x looks like so. We're looking between 3/4 and 15/4. Notice it's not a super accurate picture. I'm not having every single point placed exactly where it is or defining every single point. I'm just getting an idea in my head. And so it is this region in green that we are rotating about the x-axis. So we're going to have the other half of it is down here. And so we need to find our area. I'm going to start off very similar to how I did in arc length. I'm going to start by defining or finding my dy dx. I need that inside of my integral, so let's start there. So the integral dy dx would be 1/2 x to the negative 1/2. And then I also know that I need dy dx to be squared inside my formula. So I'm just doing a little bit of the hard work before I ever go plugging into my equation. So our dy dx squared would be 1/4 x to the negative 1. So now let's go ahead and set up our surface area. Well, we need the integral, and we are going from the lower limit of 3/4 to the upper of 15/4. And we are going to have our 2 pi times the y, and the y was just the original equation. That gave us that height at any given point was just the function. So the square root of x times 1 over 4x to the negative 1 dx, because remember this was already the dy dx squared. So we have our 2 pi, our y, and this is not right. Let's try that again. We need not just the dy dx squared, we need the square root of 1 plus dy dx squared, so that's going to be the 1/4 x to the negative 1. Then we have our dx, so that looks better. And so let's work on simplifying this integral. We can pull out the 2 pi, 3/4 to 15/4. Square root of x times the square root of 1 plus 1 over 4x dx. So here we have some sort of, this is a more complex integral, so we need to figure out something to do with it. What I do recognize is that everything is under the square root, so what I could do is I could just go ahead and bring that x into my square root. 3/4, 15/4. We'll have the square root of x plus x over 4x dx. And so then we see that the x's are canceling. Anytime we have things under the square root and they're being multiplied, we can just multiply what's under that square root. And so now we can simplify this to 3/4, 15/4, square root of x plus 1/4 dx. And so now this is something we can easily integrate. The antiderivative of the square root of x would be x plus 1/4 to the 3/2 power, meaning I need a coefficient of 2/3. Now, the derivative of the inside is just 1, so I don't have to really think about it in terms of a very complex chain rule. We're going from 3/4 to 15/4. So I'm going to go and take care of the coefficients. That would be 4 pi over 3, and then I'm going to plug in. So I have 15/4 plus 1/4 to the 3/2 power minus 3/4 plus 1/4 to the 3/2 power. So these work out really, really nicely. 15/4 plus 1/4 is 16/4 or 4. And then 3/4 plus 1/4 is 1. So if we take the square root of 4, that's 2, and then cube it, that would be 8. Square root of 1 is 1, and then cube that, that's still 1. So we get a 1, 8 minus 1 on the inside of our parentheses, which is 7. And 7 times 4 is 28 pi over 3. And that would be our answer. Now, and again, about every section that we've had in this chapter, we've seen that we have to have equations for not only a y is equal to, but an x is equal to. What if we were instead revolving around the y-axis? We're going to have to do things slightly differently. So let me go ahead and just take this formula right here. I'm going to take this whole thing and copy it over, and we'll see what we can manipulate. All right, so if we want to revolve the curve y is equal to, around the y-axis, rather than it being a y is equal to equation, it's going to have to be defined in terms of x. We don't have the flexibility that we did on volumes of having a different formula that will allow us to solve x is equal to if we're trying to revolve around the x-axis, or y is equal to around the y-axis. We have to have the matching equation. We have to, if we're revolving around the y-axis, we have to have an x equals. So let's think about what this is going to change. Well, if we now have the equation x is equal to gy, that means our height element, if we're revolving around the y-axis, would be g of y. And that means the derivative we would be finding is a derivative of that g function. And if we're revolving around the y-axis, we're differentiating now with respect to y. We're looking at the heights changing with respect to the y. in our second format of the equation, or our second format of the formula. We're now looking at x is giving us the heights, and we'd have to be looking at the derivative of x with respect to y. We're differentiating everything here with respect to dy, or we're integrating, I should say, with respect to dy. And so that would be our second form of our equation. I should also change my limits to not give the indication that they will be the same. We have to look at the y values now, so we're going to be integrating from c to d. And so we'll do an example with these. Let's find the area of the surface generated by revolving x is equal to 1/3 y to the 3/2 power minus y to the 1/2 power for y values between 1 and 3 about the y-axis. Alright, so the first thing I'm going to do is I'm going to start with my graph. And if we look at this, we might realize, oh, this is going to be a problem to put into the graphing calculator because this isn't a y is equal to equation. That's what the calculator deals with. So you could use something like MATLAB or Maple or Wolfram Alpha, something like that to graph it. It can also use the calculator to give us an idea what it would look like in terms of an x equation, just kind of rotate it accordingly. But whatever method we use, we're going to get an equation that looks like this. So we're taking this region from 1 to 3, and we're rotating that about the y-axis. Now we also are noticing this is in that negative region, and so what that's leading me to believe is that we should end up with a negative integral initially. And so we might have to, remember, if we're looking for surface area, we don't care if it's positive or negative in the positive or negative territory, we just care about the absolute value of. So we might have to take the absolute value of this. Now what makes it really easy is that whole area is in the negative space, and so we don't have to worry about integrating over two different regions. We're just going to take whatever our answer is. We better get a negative, and we're going to make it positive. So the first thing that I need to calculate, though, is my dx dy. So if we take the derivative of our equation, the 3/2 multiplies to the front, we get 1/2 y to the 1/2 power minus 1/2 y to the negative 1/2 power. And I'm just going to go ahead and find the derivative of this thing, or I'm going to take the derivative and square it, so that way when I put in my equation, it'll be really easy. So we will take this 1/2 y to the 1/2 minus, let me factor out that 1/2 too, that'll make it easier, minus y to the negative 1/2, I'm going to square it. Just take that 1/2 out, and that will make the calculation a little bit easier. So then when I square the 1/2, I get a 1/4. I'll FOIL out this other part, so we get y to the 1/2 times y to the 1/2, that's y, minus 2y to the, this will be actually just gone, y to the 1/2 times y to the negative 1/2 is just 1, and then plus y to the negative 1. So there is my derivative squared. So at this point we can go ahead and set up our surface area equation. So we'll have the integral. The y limits, it told me, were from 1 to 3. We would have our 2 pi times the x, which is the equation, the 1/3 y to the 3/2 minus y to the 1/2. And make sure that's right. Yep, that looks good. And then we're going to multiply that by the square root of 1 plus 1/4 negative 2, skip to y minus 2 plus y to the negative 1. And so this square root portion is just identical to our arc length from the last video. And so I'm going to do a few things here. I'm going to go ahead and pull out the 2 pi. I'm going to integrate from 1 to 3. of 1/3 y to the 3/2 minus y to the 1/2. Our square root, I'm going to do a little bit of work with this. I'm going to, for one, get a common denominator. We'll start with that. Let's get the common denominator between these two things, which will have 4 plus y minus 2. And that's really plus a 1 over y. And now all of this is being multiplied by the 1/4 power. Let me squeeze that in right in the front there, dy. And so the reason I wanted to get that 1/4 out of there is because now I can actually take the square root of the 1/4. 1/4 is a common factor. And I can take the square root of 1/4 very easily. It's 1/2. So that 1/2 I'm going to pull out and cancel with the 2, so we just get pi now. So this 1/4 right here, take the square root of it, it's 1/2, and then because it's now outside the square root, we can pull it to the front of the integral. 2 times 1/2 is just 1. So we have 1/3 y to the 3/2 minus y to the 1/2. None of that's changed. Our square root, I'm going to do a couple things now here. I want to get a common denominator with what's left in the parentheses, so they all need a y on the bottom. I'm going to have to multiply these 3 terms by y, and actually the 4 minus 2, I can simplify that to just 2. So I can write this as a y squared, clean that up a little bit, y squared plus 2y plus the 1. So we had to get this y over y, so we multiplied y on top and bottom, it became y squared over y. 4 minus 2 is 2. We multiplied that y on top and bottom, so 2y, and then the plus 1. And so now what we see is that the numerator can be factored. As it was, so y to the 3/2 minus y to the 1/2. The numerator can be factored as a y plus 1 squared. It is a perfect square. We saw something very similar to this in our arc length video, where we were able to get a common denominator. We were able to write a polynomial that could be factored in terms of a perfect square. So now we can take the square of both of those, numerator and denominator, and apparently when we square the numerator, because it is a perfect square, it just becomes itself. So we have pi, the integral from 1 to 3, 1/3 y to the 3/2 minus y to the 1/2. The numerator y plus 1 over the square root of y dy. And keep in mind these y to the 3/2, those are just square roots, or the square root is just a y to the 1/2. So we can simplify now because we have independent factors, and we don't have a messy term under that square root. It's just a simple y. So I can divide both of these terms by the y to the 1/2 power. We'd have 1/3 y minus 1, and we have a y plus 1 dy. And now our square roots are completely gone. It's turned into a very pretty looking problem. And so we do still need to multiply. Once we do that, we'll be able to integrate this very easily. So we'll have 1/3 y squared. 1/3 y minus y will be negative 2/3 y minus 1 dy. And so at this point, we have something we can integrate very easily. 1/9 y cubed minus 1/3 y squared minus y. We're going to integrate that from 1 to 3. So we'll have pi times 1/9 times 3 cubed minus 1/3 times 3 squared minus 3. Throw an extra set of brackets around this so I can subtract off the 1/9 1 cubed minus 1/3 1 squared minus 1. Yeah, that's good. Close that and then close our brackets. And start simplifying this. We'll have 1/9 times 27. 3 cubed is 27, so that'll give us 3. Minus 9 times 1/3 is 3 minus 3. Minus, we'll have a 1/9 minus 1/3 minus 1. So the front term is just cleaning up to be a negative 3 minus 1/9 minus 3/9 minus 9/9. And so this would be 3 and 9 would be 12/9. This would be a negative 11/9. So we need all ninths here. So 3 is 27/9. 27/9 plus 11/9 would be a negative 16/9. And so we would get the integral negative 16 pi over 19. But we said at the beginning we expected this to be a negative area. And so really we needed to be taking the absolute value of this the entire time. I didn't write it there just because it'd be a lot to write, but we did need the absolute value the whole way down because areas are always positive. And so when we take the absolute value of this, we get our area to be 16 pi over 9. And there's our surface area. So surface area is like with arc length, very formulaic. We need to know that formula, but once we have that formula, it's just kind of plugging and chugging. We got to know how to solve the integral, but it's just plugging in it and solving.